In this video, we're going to look at finding an estimate for the area trapped under a curve. I'm going to start off by drawing three different graphs. The first one I'm going to do is part of a graph y is equal to 2x. So y is equal to 2x will look something like so. So let's go ahead and write this on. Y is equal to 2x. We can see that this is a linear graph as it's a straight line. I'll do another one. I'll do y is equal to x plus 1. So I'm just choosing particular graphs just to give you an idea of how to find the area under these. So y is equal to x plus 1. Finally, I will draw an example of a velocity time graph. So it might look something like so, and then we might have something like that. With a velocity time graph, we will have the time here, so the time in seconds, often in seconds, I'm going to put it in seconds, and then the velocity, and this is going to be meters per second. What I'm going to do is look at finding the area trapped under these graphs. When we say the area trapped under the graph, we mean the area between the line and the x-axis. So on the first one, what I'm going to do is find the exact area under the graph from the point where x is equal to 0 to the point where x is equal to 2. All I do is simply go ahead and create a right angle triangle. So if I draw a perpendicular from the point now where x is 2, we can see either by using the equation or by reading off the graph that the value of y will be 4. So this point is 2, 4. What I'm going to do is find an exact value for this area right here. So what we can see is that we have now a base of 2 units and a perpendicular height of 4 units. So the area is going to be area of triangle, which is base times by height divided by 2, and that is going to give me 4 square units. So nice and straightforward. You're just simply finding the area of a triangle. What I'm now going to do is go to the graph y is equal to x plus 1, and we're going to find the area trapped under the graph between the values where x is equal to 1 and x is equal to 4. This time, instead of drawing a triangle, I'm going to draw a trapezium. You could have drawn a rectangle and a triangle, but the general convention when we're finding the area under a graph is to draw a trapezium or a collection of trapezia. Trapezia is just the plural of trapezium. So that is going to be the trapezium that I'm interested in. If we look at the dimensions of this trapezium, we can see that when x is 1, we've got y is equal to 2, either reading from the graph or using the equation. So this height right here is 2. When x is 4, y is going to be 5, again, either from the equation or from the graph. And we can see now that the difference between the x-coordinates, which is going to give us our perpendicular height here, is going to be 3 units. It's a little right angle here. When we have a trapezium, and I'll just draw this up, let's go ahead and draw a trapezium. If we have the two parallel sides and label these A and B, so let's put A just here and B just here, and we have a perpendicular height, so the perpendicular height is going to be at 90-degree right angles to those two lines. This is the H height. We can say that the area of this trapezium is the top plus the bottom divided by 2 multiplied by the perpendicular height. So if we look at the area under this particular line, and you might think, well, I could have just cut it off here and done a rectangle and triangle. You could have, but as stated, generally speaking, we would use a trapezium. So we would have now the 2 plus the 5, that's the A and the B, these are the two parallel sides, divided by 2 multiplied by the perpendicular height. 7 divided by 2 is 3.5. 3.5 times by 3 is going to give me 10.5, and that's units squared. Again, you could back that up, finding the area of a triangle. Right, so there we go. What we're now going to do is look at a velocity time graph. With a velocity time graph, the area trapped under the graph is the displacement. That's one of the fantastic things about velocity time graphs. There is an extended tutorial on velocity time graphs on the site if you do want to watch that. So let's have a look at what we've got. So we're going to find the displacement, which essentially is the distance travelled. This one right here is going to be 2, this is going to be 5, and we have a perpendicular height of 3. So again, all we're going to do is work out that. So the area is going to be 2 plus 5 divided by 2 multiplied by 3. So as we can see, same as what we're going to get here, and that is the exact displacement. And if this was a particle or a car, that's the displacement. And that is going to give us now 10.5, and that will be meters. So we can find the area trapped under a velocity time graph and give it as the displacement or the distance travelled. It's pure coincidence that this is 10.5 and this one is going to be 10.5 as well, because I could have, if I wanted, I could have done a different x coordinate. I could have done from 1 to 3. So you're thinking, well, I come to watch a video on the area trapped under a curve and an estimate for it. What we're going to do is use a very similar technique by creating a trapezium or a number of trapezia by having chords. So what we'll do is look at creating those trapezia on a basic example. In part A of this question, it says draw the graph of y is equal to x squared plus 2 for x between 0 and 3. And then in part B, it says using 3 trapezia, estimate the area under the curve of y is equal to x squared plus 2 for x between 0 and 3. Not all questions in exams will be structured like this. Some might be more explicit and do it step by step. But we may as well go ahead and just learn how to do this. So if you can already draw the graph of y is equal to x squared plus 2 for x between 0 and 3, go ahead and do it. If not, just draw a table of values. So if you wanted, you could do it. If you said, well, I'm not really comfortable doing this, let's do a table of values. If you are comfortable, please feel free to do it. I would prefer to just draw it, but let's make this accessible so everybody can do it. So if x is equal to 0, well, 0 squared is 0, plus 2 is going to give me 2. If x is equal to 1, 1 squared is 1, 1 plus 2 is going to give me 3. If x is equal to 2, 2 squared is going to give me 4, 4 plus 2 is going to give me 6. And then if x is 3, 3 squared is 9, and then 9 plus 2 is 11. So we've got these points that we can plot. So let's go ahead and plot those. So our first one here is going to be 0, 2. Then we're going to have 1, 3, which is going to be just here. We're going to have 2, 6, which is going to be just here. And we're going to have 3, 11, which is going to be just here. What we have is a parabola. We have a sweeping curve. So unlike before, and this is only going to be as good as my hand and can do on this particular tablet, remember a parabola, a quadratic graph, is a sweeping curve. It's not a collection of lines. It's a nice sweeping curve through these points. So let's just tidy that up very slightly. Again, I'd like not to be. It's like writing on this tablet. It's like skating on an ice rink. It's really, really, really tough. So what we got is something like this. Just looking not an awful lot better. So what we're going to do is that's the graph, a parabola. What we're going to do in part B is using 3 trapezia, estimate the area under the curve between these values. Let's introduce this idea of a chord. A chord is going to be a straight line that connects the top of these points. So it's going to form the top of my trapezium. So if I need 3 trapezium, that's nice and straightforward because I've got 3 of these intervals. I've got 0 to 1, 1 to 2, and then 2 to 3. If I needed to do 4 trapezium, I'd have to do it from 0 to 0.75, 0.75 to 1.5, 1.5 to 2.25, and 2.25 to 3, because I'd have to split 3 into 4. If I needed to do 5 trapezia, then I'd need to split the 3 by the 5, which would give me trapezia of height 0.6. So it'd be 0.6, 1.2, 1.8, then we get 2.4, and then 3. So let's go ahead and just construct these. I think it's important while I'm doing this to say that the more trapezia we create, the better the approximation. Remember, this isn't going to be an exact area because what we're doing is making a trapezium over the top of a curve. And when the curve opens this particular way, we're going to have an overestimate for our value because we can see that the chords I'm creating between the 2 points is going above what should be a nice sweeping curve. Again, it kind of detracts from the quality of what I'm doing because my curve is so bad, but hopefully you'll get some idea of what's going on. So it'll look a bit like that. And as you can see, that should be a nice smooth curve there. So what we have are 3 trapezia, and this will give us now, each of the areas of these will give us the values that we need. Later on in your studies, you will encounter the trapezium formula, which does this very quickly for you, but we're kind of doing it, we're doing it by making these. So what we do here, if we look at these points, we have the point here, when x is equal to 0, y is equal to 2. When x is equal to 1, y is equal to 3. We've generated these in the table. When x is equal to 2, y is equal to 6. And when x is equal to 3, y is equal to 11. So what I can do is write now the parallel sides on here, that this is going to be 2, this one is going to be 3, this one is going to be 6, and this one is going to be 11. We know that the perpendicular height of each of these is going to be 1, because that's the distance or the difference in the x-coordinates. So all I need to do to work out the area of this trapezium, like we did before, we add the 2 parallel sides. It's 2 plus 3 divided by 2 multiplied by the perpendicular height of 1. It won't always be 1. As I said before, we might have that that's 0.6. The interval might be 0.6. So if we look at this, 2 plus 3 is 5. 5 divided by 2 is going to give us, what's that, 2.5, 2.5. So this one has an area of 2.5. This one right here, what we've got is the 3 plus the 6. We divide that by 2 and multiply it by the perpendicular height. Convenient that it's 1 here. That's going to give me 9. 9 divided by 2 is 4.5. So the exact area of this trapezium, which is going to contribute to the estimate for the area under the curve, is 4.5. If we look at the third trapezium, what we'll see is it's 6 plus 11, and then we divide by 2 and multiply by the perpendicular height, which is 1. 17 divided by 2 is going to be 8.5. So all we need to do at this particular point is simply add up those numbers. So if I add these up, what do I get? 7, add in 2.5 and 4.5, that is going to give me 7. And then if we add 7 to 8.5, that's going to give me approximately 15.5. Well, that does give me 15.5, and our approximation to the area under the curve is 15.5. So the exact area of the 3 trapezia sum to 15.5, so that is my estimate. Hopefully you can see why if I changed the number of trapezia, it would get closer and closer to the curvature of this, or the curve, the actual shape of the curve. At the moment, this is quite crude. But if we'd only taken 1 trapezium, what we would have got is a really crude example, because our chord, remember the chord is a straight line between the 2 points, would have gone there. And we would have had this massive overestimation as a result of not being close to what the curve looks like. So that's how we do it. And just out of interest, while we're here, again with this course, I don't know what they may ask, but with the curve opening upwards, we'll get this overestimate. If we have now the curve opening downwards, so for example, if this was a negative parabola, we might get something that looks like that. If we went ahead and looked at trapezia for this, let's put our first one just here and our first one just here. So that would go somewhere like that. This would be under the curve. If I put my next one just here, these are going to be equal widths apart. So this value of h will always be the same. We can see now by creating these, and let's do one more, something like that. That looks about the same. If I found the area, that's not a great, let's straighten that up down there. If it's curving downwards like a negative parabola, we can see that our estimate is going to be slightly less than the actual value. And again, later on in your studies, you will look at techniques to actually find the area. We say that it's the integral of the x squared plus 2 between 0 and 3. But again, that's beyond the scope of this particular course. So hopefully that's helped out. Let's say we did 6 trapezia. So if we did 6 trapezia, what we'd end up with is splitting them by half, just there, and we would get a much nicer fit to the curve. So there we go. That's an estimate for the area trapped under the curve between 0 and 3. Right, let's do another one. So we got a velocity time graph below, and it shows some information about the motion of a particle. So we got time in seconds and velocity in meters per second. We're asked to estimate the displacement for the particle between t is equal to 2 and t is equal to 3. So this is time is equal to 2 and time is equal to 3. So we can see yet again it's going to be an estimate because we've got a curve. When it's a collection of straight lines, it's easy because we can just build those up. But again, all we need to do is 1, and we'll do 1 trapezium. We're not told that we have to do, in fact, let's just change that. Let's make that black. Let's put this line just here, and that's what we're interested in. So we go from t is 2 on the x-axis, or the t-axis in this case, x is 2 and x is 3, or t is 2 and t is 3. And we go ahead now and draw our chord. I'll put it in black. I may regret this, but there we go. So that's an estimate. You can see that our answer is going to be slightly under. The reason it's going to be slightly under is because this is curving downwards. So again, we've got a perpendicular height here of 1. If they'd asked me to go between 2 and 4, my perpendicular height would have been 2. That is 1. So what we've got is these values right here. So if we look at this and we read off, we can see that this is approximately 3.2 high. That looks about there. And this one is approximately 2.2 high. So all we do is say now an estimate using the area of a trapezium is going to be 3.2 plus 2.2 divided by 2, and then we're going to multiply this by the perpendicular height of 1. So what's that going to give me? That's going to give me 5.4. 5.4 divided by 2 is going to give me 2.7. So what we can say then is that the displacement is going to be 2.7 meters as an estimate. It'll be slightly more than that because what we've not done is factored in this little sliver just here. If you wanted to make this more accurate, what we could have done is, and let's just go ahead and we'll steal this and copy this and make a more accurate estimate. Let's say instead of doing 1 trapezium, we did 2 trapezia. So we went from just here. Let's make that black. I don't know why I prefer the pink line, but it's just not working on this particular thing. So if we took now this at 2.5 and put that there and put that one at 3, let's do that. Then what we'd have is something that looks like this, and you can see how much neater that is and how much closer already. Not brilliant, but again, it's a better. If I put 5 trapezia in there, it'd be even nicer. So again, all we would do is simply go ahead and work out the area of each of these. So we know that this one is 3.2. We know that this one is going to be 2.2. This one just here looks to be about that's 2.8. Let's even go for 2.75. So 2.75. And that's all we would do. These now are 0.5 and 0.5. So the area of this one, the first one, is just going to be 3.2 plus the 2.75 divided by 2 multiplied by 0.5. This one just here is going to be the 2.75 plus the 2.2 divided by 2 multiplied by the 0.5. And if we went ahead and added those up, we would see that it would be a greater increase on the displacement, the distance covered. In fact, let's just do it to find out what it gives me. So on that, and with the trapezium formula there is a much quicker way of working this out. 3.2 plus the 2.75 divided by the 2 multiplied now by the 0.5, and then if we add to that now, we'll add to that the 2 2.75 plus the 2.2 divided by 2 and multiply that by 0.5 times by 0.5, and that is going to give us now, what's that going to give us? 2.725 versus, let's just write this in, 2.725, and that will be meters. Remember, displacement is given in meters if we're working in t seconds, time seconds, and velocity meters per second, versus 2.7. So area trapped under the curve, you simply find the corresponding y-coordinate when you're given an x-coordinate, draw a chord between the 2 points, create a trapezium or create a number of trapezia, and simply sum the areas for an estimate. But do remember, it's an estimate. The more trapezia, the more accurate your estimate.